Hello everyone, we are back on air. Welcome to the Azure Function series. Today we are talking about the world of durable functions application patterns. Let's get started. The first pattern we will explore is function chaining, which is a straightforward approach where one function's output serves as the input for the next function. This pattern ensures a strict sequential execution of tasks. This is exactly the pattern we used in our first video with order processing example, which followed this model. At the beginning of the process, we check the inventory. If this function returns true, we proceed to the payment process, and if the payment succeeds, we ship the order. Each step is executed one after the other, maintaining an ordered flow of execution. Now let's move beyond function chaining and explore more advanced durable functions patterns. When dealing with scenarios where multiple tasks can be executed concurrently, we leverage the fan-out, fan-in pattern. Instead of processing items sequentially, it executes functions in parallel and then waits for all functions to finish. Often some aggregation work is done on the results that are returned from the functions. Returning to our example, the first thing we should do is change our input parameter for the orchestrator so that it accepts an instance of an order which can contain multiple items. Let's not change the user input and only retrieve order ID from query parameters, and after that construct an order with static 2 items. Just like that. Then in our orchestration logic, instead of checking inventory for each item one by one, we can use fan strategy. In the fan out step, we will call multiple activity functions in parallel for each item by capturing all the order item IDs into a variable. Next, we use a list comprehension to combine all the tasks for inventory checking. But instead of order ID, we will use an item ID here. Then we use a new durable functions feature, the context task all function, passing the list of activities to be awaited. In the fan-in step, we will aggregate the results before processing to the payment by checking if all items are in stock. That's a core principle of this pattern. Let's run it and see how it works in action. When we start debugging, we can see that the check inventory function is triggered only when task all is executed. As expected, both items are in stock, and we can continue execution. Alright, the next durable function pattern we are looking at is Async HTTP APIs. This pattern is all about handling long-running operations without making clients wait around for the response. Instead of keeping a connection open, we let the client trigger a process and then check back later with a special endpoint to see if it's all done. Now let's go back to our order example. External systems often need to check the order status, but we don't want them to just sitting there waiting. That's where these patterns come in. The idea is simple. The client makes a request to start the order process, the function immediately responds with a status URL where the client can check progress, and the client polls that URL until the order is processed. And the best part, durable functions handle all the state tracking for you. You don't have to build any custom status management. In the previous video, I've shown you that from a HTTP starter function, we retrieve a status query getURI, which uses an orchestration instance ID and can serve to track a function execution status. Let's retrieve it again by running the task. Here it is. And when we open it, we'll see the status. No need to write any extra code for this. Also, we can implement an endpoint that will generate for us a response that lets client retrieve some specific response based on a function status. The key here is client getStatus function, which checks the status of the running task and allow us to perform any action we need. Based on this, it basically extends your options to operate with function status and response as you want. But polling is not always ideal. If you want to avoid constant requests, you can send a webhook notification instead. That way, as soon as order is processed, The system pushes an update to the external service. The next thing we will discover is the monitor pattern. This is what you need when you're dealing with a process that needs to keep checking something until a condition is met, unlike the Async HTTP APIs pattern, where a client needs to initiate a request. Think of it like waiting for a package to arrive. You don't just sit at the door all day. You check the tracking updates every now and then, and it's always up to date due to monitoring. Now, in the order processing example, this pattern comes in handy when we need to keep checking an external system until an order is confirmed. Instead of waiting around or keeping a connection open, we can just check in every few seconds until we get the result we need. Here's how it works. A new order is placed, and we start monitoring it. The function keeps checking the order status. Once the order is confirmed, we move forward. But also, if too much time passes without confirmation, we stop checking to avoid wasting resources. And here's how that looks in Python. We need to introduce an activity, which will pretend to be checking order and return processing status this time. And one more, for customer notification about confirmed orders. Then we have a new starter function, which is extended with two parameters, polling interval and the expiry time, which will be used in the orchestrator for monitoring. Everything else is similar to the previous example, and the big one here is new orchestrator function, which uses polling interval and expiry time to operate with while loop and constantly check for order status until monitoring expires or as soon as it succeeds, and customer will be notified and while loop stop. Let's see it in action when we run it on our hard-coded status, which is processing. It will just continue running each 10 seconds until it expires. But as soon as we change it to confirmed and run it again, it will automatically break the loop and return a successful response. You may ask, why is this better than a simple timer? There are a few reasons. You are not stuck with a fixed schedule. You can check more or less frequently as needed. It keeps track of everything for you. So you don't need to build extra logic for tracking state, and you can monitor multiple orders at once and each one runs independently. Let's explore the next pattern. Sometimes an automated process just can't do everything on its own. Some decisions need a human touch. A good example, order verification. Let's say an order needs manual approval before it can be processed. Maybe a manager has to verify it, or a fraud check needs to happen. We can't just wait forever, so we'll set up a timeout mechanism. If approval doesn't happen in time, we escalate or cancel the order. Here's how it works. The system sends a request for approval, it waits for a response, but not forever. We'll set a timeout. If the approval comes in on time, we continue processing. If time runs out, we escalate. Maybe send it to another person or cancel the order. Here's how that looks in code. We have new updates in the orchestrator logic, which now adds time to wait for external events, order approval for 72 hours, and as soon as this event will be triggered, the function will continue execution based on the result of validation. If it's approved, order will be shipped. And we have a human trigger here, which you can link to a button on your website for administrators to validate orders. Let's run it now. Starting with order processing logic, we can see that it stopped execution and waiting for human response, which is implemented as a separate route in our code. When we trigger it with approved status and current instance ID, which is taken from starter function, it will continue and ship the order, as we expected. Also, if we try to do same operation with order shipment now, triggering a new order process, but instead of custom approval event route, we will use a built-in API that provides possibility to raise an approval event by calling this HTTP endpoint and sending approved as a value. We can reach the same result as shown on your screen. This event was correctly picked up and order shipped. And the last one that we will cover today is aggregation pattern. In many systems, data doesn't come in neatly, all at once. It arrives in pieces, sometimes from multiple sources, in batches, or even over long periods. The aggregator pattern is designed to handle this by continuously collecting all updating data into a single, addressable entity. However, implementing this with traditional, stateless functions can be tricky. Concurrency issues arise when multiple processes try to modify the same data at the same time. Plus, ensuring that the aggregator runs on a single VM without conflicts can be a challenge. That's where durable entities come in. They provide a simple, stateful way to aggregate data reliably without worrying about concurrency or infrastructure constraints. Let's say we want to keep track of total processed orders and revenue. Instead of updating a database for every single order, we can use a durable entity to maintain a running total. Here is how we can define the order stats aggregator. It retrieves current state from entity context and check if operation is at order, then takes an input and updates entity state with it, and sets this updated state as the result of the operation using setResult function. Whenever a new order comes in, we need to trigger this HTTP-triggered Azure function, which is sending a signal to entity order stats with received order revenue. Let's try to run it a couple of times to see how our state is changing. As you can see, each time we're receiving a new order quantity and new revenue. We are wrapping up at this point. All examples are available on GitHub, link in the description. Thanks for watching and see you soon!